Hi, welcome to this first tutorial of the workshop, and we will now take the material, poplar wood, and think about its characteristics in terms of geometry, and especially the fact that it consists of developable surfaces. So surfaces, you see them a lot in architecture when we do facades or structure, and it is good to know what are the different types of surfaces and what are the characteristics, constraints, and what we can do with them. So let's start with the idea of geometry. You have differential geometry. The differential geometry is kind of the infinite precision geometry. For example, a surface is an infinite set of points, whereas in discrete geometry, we will evaluate this surface with only a few points, and we link them together, we make a mesh that represents the surface. This way we can make computations much faster and simpler. And also you have a big difference between the Euclidean geometry and the Riemannian geometry. So if you want to describe a surface with two coordinates, then you can only get a flat surface in Euclidean geometry, whereas in Riemannian geometry, just now imagine that the space is curved, and so with only two coordinates, you can get in the other dimension. So for example, if we take this surface in Euclidean geometry, we need three coordinates, we need three dimensions to get to a point. But now imagine that it's a set of mountains and you are hiking, and you will really not describe your place in terms of three coordinates. Maybe you prefer to speak about your path, the way you take. It is more convenient to indicate it with coordinates on a surface than coordinates in space. It is also useful when you want to describe very complex surfaces, to use Riemannian geometry, or when you want to describe space itself, but we will not do this today. It is also convenient when you want to describe the intrinsic characteristics of surfaces, which are basically the curvature it has, and this is what we are interested in today. So as we just said, you can point any point of a surface with only two coordinates, and these are called u and v parameters in rhinoceros. When you evaluate a point, then you can get an osculating plane and a normal vector, which defines a frame. If we go back to only one curve, then you can evaluate it with one parameter. And as it is still in space, you have a notion of curvature. And if you imagine that you are walking on the curve, then you can imagine how you get up or down and how you turn right or left. And now let's see that this curve is on a surface. And you can still get the same point and the same direction, but now you evaluate it on the surface and you don't have the same curvature. And here, why you don't have it is because you take in account the frame of the surface and not the frame of the curve. And a very specific curve is the geodesical curve. So it means, in fact, that the curvature, if you take this point in this direction on the surface, is the same as the curvature in this point and this direction of the curve. Which, in other words, means that you just get up or down, but you do not turn right or left in the plane of the surface that we evaluate. Now, another type of curves, even much more important, is the principal and the principal curvature, which are the maximal curvature and the minimal curvature. And now you still have a point, that you evaluate, and from this point you have the right to take any direction. You can turn wherever you want, but you just want to get down as much as possible or up as much as possible. Let's say if you get downhill, then it is the minimal curvature, and if you get uphill as much as possible, then it is the maximal curvature. Now, if you multiply these two curvatures, you get the Gaussian curvature. And this is really the intrinsic characteristic of the surface. Here you can see that we can establish how the surface is curved. And now we are more interested in the gray area, where it has no curvature, where the curvature is 0, because it is where the surface is developable. So for example, take the surface on top and the surface on the bottom. The surface on the bottom is now purely developable. You see that we can read that it is developable in different ways. For example, on the left, as we just saw, we do it by multiplying the two principal curvatures. On the middle, we will see it just afterwards, but it is a Gauss map. And on the right, it is a projection of or drawing of an orthogonal geodetic net. And the thing is, if you can draw one on the surface, then it is developable. If you cannot, then it is not developable. And you have also different ways to draw a developable surface. All have in common to draw some rulings and then to make a loft between them. And you have one type, which is the tangent surface on the left. You draw a space curve, and then you do tangent from it, and then you loft it. Then you have the cone version, which is all the rulings converging to a point, then a cylinder where the rulings converge to infinity, and then a plane with, it's a cylinder in fact, but with an infinite radius. And just note that the cone can have various radius, and as well for the cylinder. Now let's just get back to this idea of the Gauss map. So you draw some normal vector on the surfaces, and then you take all these vectors and you put them starting from one single point. And if the thing it draws, if this map is a curve, then it is developable. If not, then it is not developable. So just last thing, don't confuse ruled surface and developable surfaces. Like when it has some rulings, it is not necessarily developable. Like on the right, it is not developable even if it has some rulings. But each developable surface, like the one on the left, needs to have some rulings on it. Okay, so now let's get our hands into it and go to Rhino and Grasshopper to make some tests. So here we go. I suggest that we split in two parts. First part we will do some developable surfaces from scratch, and second part we will analyze them and check if they are really developable. So let's do the first type, which is tangent developable, and build a curve by hand first in Rhinoceros. So you can do a spline curve and make sure that it sits in a space, like this for example. Import it in Grasshopper. And now we want to make some tangents on it from some point. So we will divide it to get some point. Divide curve, so that we get points and tangents, and let's put 50 of them. And now we can draw some lines with SDL, start, direction, and length. Okay, and now we have, I think, to extend them, because if we loft them now, the loft will not really work. We extend just from the start, negative 20 maybe. Or I let you put the good numbers from the scale you have. And now we can loft this. Yes, perfect. So this is a tangent developable surface. And yeah, you see that it is not necessarily made feasible with Poplar, because one thing we did not speak about yet is the fact that it is bended, and in some places the curvature is too much here, so Poplar would not resist to this. But still it is developable. Okay, let's do another type. Let's try out conical type, and we can start with a point from which we will make converge all the rulings. So we make a point here, we put it in grasshopper, and from this point we will do some other points with polar coordinates, and for that we need to give like a range of directions which goes from 0 to, let's say, a full rotation, so twice p, and we put again, I don't know, 50 of them, and yep, then we just give a length, so maybe it will be 200 again here. Yes, and so we have this magnificent corona. Sorry. And we make graph mapper so that we will give some information about the angle in the z direction, and we want the same amount, but from 0 to 1, so that these numbers could get mapped to other numbers with, for example, Bezier type of curve, and so it will output some values from 0 to 1. We will just multiply them from something that goes as it is angles, we will say p, and so like 0 to, yeah, let's say 0.5p, so that it makes half a turn. And now we can build some lines as just what we did before, but this time linking 2 points. And let's take this back from the previous definition, that we extend the line at the beginning, and then we make a loft, and here we have this magnificent developable conical surface. Cool. Okay. For the last one, the cylindrical surface, let's do something which is more likely to be a design of something, and we will try to do a volume, in fact, out of two cylindrical surfaces. For that, we'll first do a curve in Rhino and check that this curve is possible to be mirrored along the XY axis. I don't know, like this, for example, and import it in Grasshopper again, and so as I just said, we will mirror it. I will explain why just after. Oops, again on the XY plane, starting from one point here, and no, XZ, sorry. No. YZ, the last one. Yes. Okay. And now we will do an arc in one direction that we will extrude so that we get the first surface, which will be a portion of a cone, a simple cone. So for that, let's take the bounding box of this curve and that curve as well, and make a union box, and we convert it to a rectangle. Yes, here. And now we can just take the segments of it with explode command and take first one and say we will do an arc from this one. So we take the endpoints, we take the middle point, evaluate length at 0.5. We move this point up in the Z direction with a distance of something, maybe more, and we do an arc from 3 points. So we have the start point, the middle point that we moved up, and the last point. Okay, and now we will extrude this in one direction, which is if we take back the rectangle, the segments, we take the other segment, we add one to the list item, and we do a vector 2 point, and we get this extrusion here. Now we want to make another surface, which is in fact computed with the outline of the first of the plan, in fact. So let's project the plan curves on the B-rep, like surface, this surface here, and the curve is, let's put them up. The first one we imported and the one that we mirrored here, and up. We project it. Okay, the interesting point is that as we mirrored it and as we place the cylinder on the with an axis which is on this mirrored plane, it means that each point on the left curve and on the right curve we draw some lines which are by definition parallel. And as they are parallel, it means that when we loft them, it will be also a cylindrical type of surface, which is developable. So we can just do a loft between these two curves, and it will give another surface, which is by definition developable. Now we just want to get rid of the corners of the extrusion, so we will split the surface with the projected outlines, and now we still need to selection the middle one. So for that, I think the easiest way is to get centers. Okay, it should work still, of the surfaces and compare it to the center of the rectangle, so the rectangle that we built from the bounding box, and we will check the one which is the closest to this point, so that we can select the target surface, so closest point, the center of the rectangle, and the distance, like the closest one of the centers of the other surfaces. And with list item, we selection this one, and it should be the one in the middle. Okay, so just to have a more clear view, Okay, sorry, just maybe if you need to check this up, I place it to white. You can pause. Okay, and I will show you a picture of something I did, which is based on this. The design I just finished. I didn't test it yet, but hopefully if there is some wind. Well, okay, so it was popular and it worked, and this thing of combining two surfaces has the advantage of making something much more stiff than just one plate, which is quite interesting. Okay, so here are three kind of developable surfaces, but of course you can start to design with this and you can combine them. Most of the developable surfaces are in fact a combination of tangent-like surfaces, conical and cylindrical, and planar one. Okay, let's do this last thing, which is evaluating or checking if it is developable or not, which means checking what is the Gaussian curvature on each point of these surfaces. So we will do it with two different methods. The first one is just by computation of the Gaussian curvature. This will be quite simple because it is already included in Grasshopper, and it is called principal curvature. You have also the curvature analysis, which is already included, but just to explain, we will do it more manually now. Let's start with a surface which is something not developable, and so we can do rectangular surface here to rebuild, and yes, with a few points on it, and then points on, and you can just make a free shape quite fast like this. Okay, and we import this surface in Grasshopper, and I don't think this is developable, so we should see some interesting curvatures. So let's evaluate this surface in a few points. No, sorry. As at the end we want to display it, we need to make a mesh. So here I will use the mesh breps from Caramba. If you don't have it, you can also use the mesh brep here, but I think this one will be better now. And I think with the scale, maybe something like 50. You can check the edges, mesh edges, to see if it's a good resolution. Yes, it looks good. And we will take the surface, and we want to make some analysis on each point of the mesh. And for that, we need to know where the points are on the surface. For that, we need to deconstruct the mesh, so that we get all the vectrices, and all the vectrices we need to get the surface closest point from this point to this surface, which gives us some coordinates u and v to evaluate the surface and the curvature of the surface. Now we get the principal minimal curvature and the maximal curvature, and as the Gaussian curvature is a product of them, we just make a multiplication, and this will be the Gaussian curvature. Now we just want to display it on the mesh, so we will use mesh colors. We take back, maybe I'll put it up there. We take the mesh, and we want to put some colors, and these colors will be informed by the Gaussian curvature. So we do a gradient. We evaluate the gradient with the values here, and as the values are generally really low, you just have to find the good scale of representation. I think this is more or less this, and it should go from a negative to a positive curvature maximums, extremums. And I think we are ready to display it. And we just need a good preset color. Okay, I'll let you put the values you like, but let's put the green as developable surfaces. This will be negative curvature, so anticlastic and synclastic positive curvatures. To see it better, let's display off here. Okay, just move this. Okay, so now we can visualize more the area which are curved positively, which are curved negatively here, and which are not really curved here in green, which is what we are targeting for developability. Okay, and let's do now the gauss map of this. So for that, we take the same surface and we take, we will divide it. We don't do a mesh this time, we just divide surface. And okay, 10 by 10 is good. And we draw some normal vector. So vector display. I think we need to scale them up, or in the scaling at least. So multiply them by what you need to multiply so that they are visible. Yes. So we get the vectors, and the idea of the gauss map is to project all these vectors from a single point. So yes, let's put manually a point somewhere in the middle of all these surfaces. Oops. And we can just do this, of course, but in order to be more visible, I would just do average, weighted average between each point here. Okay, we need to graft it so that we have only one element by branch, and so this point, between this point and that point, we will do a weight between 0 and 1, and the complementary weight of it, so 1 minus it, and so we put the weight, no, sorry, insert item. So we take the points and we want to insert this point. You will just understand why after, and we want to place it in the list, and between these two, I just show what happens there. So we have each time the reference point, which is this point, and the point that is evaluated on the surface, and we want to do a weighted average, so one value and its corresponding value to get to 1. And so now we get some points, which means that it can move from the points on the surface to the point, the reference point, which is just a trick to visualize it better, and we can show it like this. Yeah, and one last thing we will do is, so as we graft it, we trim the tree, and we can do some polylines between the moved points. Okay, we'll erase this. So we move the point of the distance and the direction of the vector, and we connect these points. Sorry, we trim these first, then we connect them, and we do the same with flip matrix. You will see just afterwards, I hope. Yes. Poof. Okay. Let's display this in a better way. No. And so we have our number, the surface at the beginning, and you can see like that we do all and we represent the surface on the tip of the vectors, or tail of the vectors, and we put all the vectors in one point, and now you see the ghost map. Here it is a very messy ghost map. You see some kind of curve here which correspond maybe to an area which is more or less developable or more or less flat, I think, which corresponds to this. But you see a lot of turbulences of curvatures which are not developable. Let's compare this to another surface of one that we just built before. So let's take, for example, this tangent developable. And abracadabra, it is green first from the display of this curvature here analysis. And a redundant way to analyze it, but also interesting, is the ghost map. And so we start with, oops, maybe not enough. We start with the vectors, normal vectors, and we project them to from one single point. And they all describe just one single curve, which means it is developable, indeed. Okay, so I think these are some tools to check if your design is developable or not. Then we have some ways to build developable surface, because we know how we build it that it will be developable. And of course there are other approaches. I think the first one we will do is just play with paper, because paper is developable, so you can just make models and see how it behaves. And then we will also try to simulate the paper in the computer, and we will also do some other kind of design, and we will see how it goes during the week. And of course we will also do some structural analysis. So I hope you enjoyed this first tutorial, and I'm really looking forward what we are going to do and what we are going to learn from this first step. See you!